I had a client one time that said, we need to use some AI. I said, you do? He said, yes. I said, do you want like a small box of AI or maybe a Venti, Grande, something like that? He had no idea what he wanted. He just knew he should be sprinkling AI on things. That's not how it works. That is how BI works. You can actually get a bunch of data and start looking at it and exploring, and it'll make you ask more questions. Data science doesn't do that. One data set, one set of algorithms, one answer. That's the way that you have to tell me what you want to know before I can begin applying the data and the analysis to it. Data analysis is involved in this. This means create, read, update, and delete our standard CRUD operations, programming and control reporting, business intelligence, statistics, and data mining. If you're not familiar with the difference between data mining and business intelligence, you should educate yourself on that. We don't have time to do that today. They are different. In fact, data mining is a precursor to artificial intelligence. Also, you need to know how to tell a story. In the scientific process, we define a question or we create a hypothesis. We create a repeatable test. We try to push ourselves off of the hypothesis. You never prove anything in statistics. You just prove that it's not true in some cases. And you publish your results. This needs to be repeatable, which is why notebooks, if you're not familiar with Jupyter Notebooks, that's why they're so useful, because I can give my code and results to other people. You'll see those today. Artificial intelligence is also an umbrella term and involves two major things these days. It used to involve a bunch of other things. Now it involves these two. Machine learning is the process of showing the computer lots of data, applying a certain algorithm to it, and there are many families of these, and allowing the machine to tell you, here's what will probably happen next on data I have not seen. Most of you learned to read a book by reading lots of books. You found out there were rules, you found out there was grammar, and so on in your native language. From then on, your mind had a model. You now know how to read a book you've never seen. That's machine learning. They're not quite that smart yet in machine learning, but that's the process. Another one is called deep learning, which has a different way of approaching things. And it basically deals with layers. There are layers of things that are responsible for individual inputs. It is not like the mind, but it's called a neural network. It's a very, very gross approximation of the human mind, but it works in a similar way in that different inputs are sent to different channels, and they're combined and triggered along the way to create a result. You'll see this quite often in language and vision. So much time we have today to do about that. The history is very brief. We started in 1950s with artificial intelligence. In 1985, we began to develop the machine learning. And then in 2010, we were able to do deep learning. The math underneath all these goes before the 1800s. Anna Hoffman and myself do a series on her show, Data Exposed, called Something Old, Something New. And no, that has nothing to do with my age and her age. It's got to do with the statistics and the application of those formulas to machine learning. You can watch those episodes for free online, Something Old, Something New, and you'll learn a great deal more about the underpinnings. Here's what was stated in 1956. You are so predictable that I can probably get a computer to figure out how you think. That's what they believed. They're kind of right. Humans are predictable, a human is not. And there's a whole world behind that. We started out with symbolic logic, fuzzy systems, simulations, something called expert systems, where I'd have you enter everything you know about your job. I would then perform a bunch of fancy if, then, else statements in Prolog, and I would come back with an expert system. And everybody thought that was, intelligence, and it's not. We also had something called evolutionary computing, polymorphism, and so on. We've now moved into the statistical world of machine learning, where we do inference, hidden Markov models, information theory, and quite a bit of normative Bayesian decision theory. If any of those terms are new or scare you, it's okay. I've got links to learn all of them for free in the notes here. All right, let's go talk about how you use it and where you use it. There are various families of algorithms, groups of algorithms, and this is why I need to know your problem to apply an algorithm. If I'm trying to predict how much or how many of something, like what's the temperature going to be next week or whatever, I will use a regression model. These are Very popular. There's linear, there's nonlinear, there's all kinds of regression. This simply means looking at a straight line, what will happen if I go one more point to the right on the straight line? It's more complicated than that, but that's what it looks like. These are very powerful, used quite often in more places than you might think. The next one is it odd? Which is an interesting thing for me to say. If you know me, you'll say, oh yes, it's absolutely odd. I always show people this group of writing implements, and I say, is that group of writing implements odd? And they begin to answer me. Well, some of these are colored pencils, so they use wax, not lead. Some of these are mechanical pencils, so you can't sharpen them, you turn them. And I say, is that odd? And they begin to try to figure out, are these odd things? And it really depends on one thing. What's the answer you're looking for? If the answer is, what's in my drawer? This may not be odd. If I'm a wax pencil company, this is odd. Do you see my point? The question determines which algorithm you're going to pick. This is called an anomaly detector. We see this quite often in fraud. We see it in medical for detection of things like cancer and so on. Another one is which category is something in. These are called classification algorithms. Many, many years ago when I was a child, we used to have these little banks, and you could put a coin in it, and it would roll down the slot until it fell in the proper hole. Anybody else have that? Okay, you're also old? Okay, good. And you're old. Okay, perfect. You used to roll these coins down to a slot. That's exactly what a classification algorithm does. It sorts the data, and it says, are these things, do they meet this criteria or don't they? There are boundaries you can set and so on. There's also something called reinforcement learning. You ever see the movie with the bad guys and they always say cut the red wire? If I was a bad guy, I would just make them all red. But I digress. Reinforcement learning says, I will do something, and if that doesn't work, I'll take feedback on it and I'll try something else. How many of you have the little vacuum cleaners? The little floor vacuum cleaners that wander around by them? Yeah, that's reinforcement learning. As it maps your house, it hits the wall and it goes, well, that's a bad idea. So it moves to a different wall and it stores the reaction to that. And then we have one that's kind of interesting because all of these to now have been what's called labeled data. What in the world does that mean? Well, labeled data means I need to show it a bunch of books and say, these are books, those are words, these are grammar, and then you can read. So I have the answer in mind. But there is a group of algorithms that don't have an answer. I just dump the data on the floor and I say, you figure it out. One of these might be something like a k-means clustering algorithm. And what this will do is I say, I want 3 or 4 centroids. I want the center of data to gravitate. So if we did this in this room, we'd have everyone stand up and we'd say, tell me everything you know about yourself. We'd put all that information in a bucket, and we would begin to find the most common 3 things we had, and the next most common 3 things, and we would begin to group each other in that way. Size, weight, sex, hair, whatever it happens to be, we would group them in that way. We don't know the answer beforehand. The computer will figure it out. This is very common. You'll see these clustering recommenders. If you like this movie, you'll like this movie. It's just clustering you with other people. My family shares a login to the video services, and so our clustering algorithm is very confused. It either thinks I want to watch a Pixar movie or something from France. All right. Okay, we'll move on. I wish we had time for questions. I really do. Let's quickly go over some of the languages and technologies you'll use for data science. One of them is R. R is a programming language. It is not a procedural language that takes the input from the other side and takes it into a variable. Okay, so it's in that kind of vein, and it works with data. It's one of the earlier ones. It comes from an offshoot of a language called S, which was a statistical programming language. Python is another language that's used quite often in data science. As a matter of fact, they keep battling for which one is used more, and it actually doesn't matter. You pick the one that has the library you need, and many R libraries are available in Python as well. If you need to learn one and you're a DBA, go learn R. If you're a developer, go learn Python. And then forget I said that because it's probably wrong, but that's what I usually find. People that know SQL can work with R very well. People that work with programming usually have no problem with Python. You can learn both even if you want. There are other platform-specific languages like MLlib or PySpark or SparkR inside things like Spark and so on. SQL does not have a predictive language, but we have put data services inside SQL Server, so that's kind of interesting. Java, believe it or not, people still write in Java. Don't know why, but they do. Any Java developers in here? No? Okay, if you want to learn Java, just tie some keyboards to your feet, walk around the yard, terminate it with a colon, and it will compile. That's wrong, and I shouldn't make fun of Java. But you can do machine learning inside Java. There are a lot of people who make a living doing that. All right. I've got some learning resources. If you want to take a quick picture of that, go for it. Get your little cameras out. You got a countdown timer here. We got to get moving. Free. All free, and it gives you a full environment to learn everything you want to know about AI. I've just gotten you a new skill, and you can make a lot of money at this, so I expect a really good feedback score. Or just mail me your raise, whichever one. You got it? Okay. Let's talk about creating a data science project. It used to be back in the day that the data scientist sat back in her office with a very powerful computer running R, and they would bring her data and they would say, what does the data say? And she would take it back to her office and disappear for days, and she would return from the mountain with 2 tablets, thus saith the data, like an iPad and like a Kindle Fire. And she would say, thus saith the data, and they would say, ooh, and that was how that worked. That's gone. The days of the single seat are gone. There's now a process that you can use for data science. There's a resource here called the Team Data Science Process. This is something I worked on and helped create with a team of people who do data science. It involves understanding the data and so on. The thing you need to take away from this particular slide is that inside data science, we do not do ETL. We do not do extract, transform, and load like we do in business intelligence. We do extract, load, and then we transform it at the last possible time. We do that because each algorithm will decide what layers of precision it needs, whether it needs to categorize things like the word orange into a number, and so on. There's actually a word for that. It's called one-hot encoding, which I think is hilarious. But at any rate, these all take different things. So you want to bring the data in and leave it as native as humanly possible as long as you can. This is data science. The reason we leave it native is because we want to make sure that when we touch the data, every time we touch it, we've changed it by observing the data, by taking, oh, that's a text one. I'm going to turn it into an integer. An integer, did you need precision? Did you need scale? And so on, right? It all depends on the algorithm you're using. At this resource, when you go here, we have a description of everything I've got here with examples, and I even included a Microsoft project plan to run a data science project, so you can download that. And I also have it in a spreadsheet if you don't have Microsoft Project. But we go through every single thing in here, okay? So I just want to kind of hit that we've got that available. Last thing we'll talk about is here, before we get into the meat and potatoes a bit, is the hybrid modeling deployments. So let me talk to you about the phases of machine learning. We gather the data in, we clean it up, we get it ready to where it can be used. Once it can be used, that's called data engineering. We simply look at it. We just look at it. We don't do anything else. We begin to chart it. We begin to graph it. We just physically look at it. There's something called Anscombe's quartet, A-N-S-C-O-M-B quartet, Anscombe's quartet. If you look that up, it's a very famous statistical example where data that looks exactly the same with mean, median, mode, average, standard deviation, all those things, looks exactly the same when you look at the numbers. When you graph them, they're wildly different. And this shows the importance of actually looking at your data. After we look at our data, we begin to create an experiment where we take various algorithms and we begin to train our model by showing it these numbers. We hold out some of the data we know the answers to. This is called the test data. We train the algorithm, and then we take one of the things we know the answer to, and we say, what do you think that one will be? I think it will be a 12. You get a score. I think it'll be a 13. You get a score, and so on. At the end, we look at our model. Okay? And the model is just sort of the Excel formula, if you will, that's created our answer. and we see how well it does. This is what we call in data science the performance of a model. Has nothing to do with performance tuning in SQL Server whatsoever. That's something else entirely. When we say something about a model's performance, we mean how good is it? And if it's very good, it's wrong. How many of you have been married more than like 5 years? 10? Okay, I've been married 36 years. If I'm always right, something's wrong, right? I know I am not. If my wife is agreeing with what I'm saying, I'm like, uh-oh, it's bad. That's a humorous example to say that if you see a model that is always right, life isn't like that. So when you get the prediction back, you also get how confident the algorithm is in that prediction. We call those things a score. So you'll say, what's the score that I'm getting back from this model? And that's what that means. It's not only the is it true or not, but it's how sure are you? And some level of unknowing is okay. That's normal inside data science. Everybody with me? Go like this. Okay, good. Now, once we've trained our model, which takes a lot of data and a lot of power, I can deploy the model because remember, you don't have all your books from school with you right now, and yet you can read a book. You've just got the model, which fits very nicely inside your cranium, to read a new book. You with me? So that's the model deployment that will do the scoring. So now I can simply walk up to you and say, can you read this to me? And you can. But I don't have to go back to your school and stand in your library amongst all your books to get that done. Does that make sense? So deploying the model can be separate and is normally separate than training the model. These terms are going to become important as we move through the session. All right, now we're to the session. I had to give you all that background to give you the session itself. And by the way, I teach like a 5-day course on this, so we're moving at fairly quick speed, but that's okay. You're probably anxious to get off to lunch, I would expect. Databases as a source or sink for data science is the most common. And here's what you do in this example. You're not meant to read this. This is just a picture. Basically, the data scientist will have a tool like RStudio or something like that, some sort of coding environment. They will pull the data out of the data sources, lots of them. They'll create a place where they can load it into this thing, and they'll begin to train the model. Once the model is trained, they'll try that experiment. No, let me use a different parameter. Let me use a different algorithm. Let me use different algorithm family. Let me use 2 algorithms, and so on. Once that's done and they create the model, that's given back to another system to score the process. So one of those sources of data can be SQL Server, or any database for that matter. But there's a bit of an issue by doing this. Well, there's a bunch of issues by doing this. The first issue, as you can imagine, is I've got to pull all that data locally. Whether I save it locally or whether I'm just making network calls, we're dealing with large sets of data. More data is better, right? To a degree, unless you're in deep learning, and then more data is better. But more data is better. We're talking large sets of data. These are not 10K calls. These are heavy. So you're pulling that across each and every time. So that's expensive. I then run my experiment and I create my trained model. Okay? Now, here's the problem we have with that environment when we did this before. So we've got all of our features. So you can see here we've got an application, we've got our experiment, we've got our training, and we've got our deployed model. And we've got the person that's going to consume the model. The data scientist at the top, she's created everything. This consumer at the bottom, he's going to actually get a score. So here's what's nice about this. Nothing ever leaves SQL Server. In the other example, we pulled everything across the network. Maybe she brought it to her laptop, throws the laptop in her car, and goes out clubbing in London. Somebody breaks into the car, and your social security number is on the dark web. This happens, it's humorous, but it happens every day, every single day, because the data leaves. It's very insecure, and the pathways to do everything is very insecure. But with SQL Server, the security boundary stays there. You can do the training, the testing, the data engineering, and the scoring all on the same security environment, which becomes very useful. And yet, the developer, the data scientist, doesn't have to learn T-SQL. They can stay in R, they can stay in Python, they can stay in Java. Let's see how they do that. We have the support for the major languages, R, Python, Java, and we've open sourced the parts I'm going to show you in a moment so you can actually create your own. You want to use Go or Rust, knock yourself out. We don't mind. We have SQL Server integration services for data engineering. Oh my gosh. If you've never played with this and you're a data scientist, when I show them what they can do inside SSIS, some of them have physically cried because it's years of their life they've had to do the same things that SSIS does with drag and drop. It's stunning. We have this available in SQL Server on premises. It's even in IoT. It's literally in the SQL Server that runs on an ARM processor, all the way out to our big iron in the cloud. And it's the same stuff. It's a complete eco-structure. We have testing, training, data engineering, reporting, and programming, all available in one place. And everything stays inside the same secure environment. It uses something called the Machine Learning Extensibility Framework, and that's where we're going to spend a little bit of our time left today. However, if you would like to learn to write artificial intelligence constructs, to do things like vision or text analytics or voice or video analysis or any kind of prediction, error correction, anything you can imagine, don't. Just don't. Don't bother. You have to go learn math. We have something called cognitive services in Azure. These are services we've already built, and there's tons of them, and we're adding to them all the time. These are done by the brightest minds around, and they're available as a service, and you simply call out to them from SQL Server, get your score, and do whatever you were going to do with it to begin with. Wow, we got to see that, don't you think? All right, let's go out to a notebook. This is a notebook. How many of you are not familiar with Jupyter Notebooks? Just raise your hand. Not familiar with Jupyter Notebooks. All right, good. So I've got a notebook here. And by the way, for those of you online, yes, shut up. The folks in the room did not raise their hands, so I'm assuming everybody knows notebooks. So if I want to do this, here's a typical AI processing system. I'm just going to use Python. I'm going to upgrade my packages. I'm going to load the packages to get my stuff that I want to do. I'm going to create my stuff. I'm going to go get from SQL Server the things I need. This is transact SQL. I'm building a string. And then I'm simply going to bring that data in, and I'm begin to do my data science in here. I'll plot it first to show it, and then I'll just do a clustering using k-means algorithms for that, and I get my information back. That's the way that looks. Looks like I've got 5 groups here that it bundled me into, and it shows the performance of the model over time as it does its work. So this is just using SQL Server with Python. Nothing new here. We've seen this. But I just told you didn't have to learn any of that data science stuff from here. So basically, I've got the full example available to you in this notebook, and this notebook's open to anyone. So I'm going to use wide world importers and just take a look at things. And what I've got is some reviews of my product. Like, yeah, you'll like this and so on. But here's the problem we have. Great product to save money. Don't worry about and so on. There's a problem here because when we speak in sentences, especially in the UK, if I were to say to you, how was lunch, you would say, not bad. In the US, this is the greatest lunch I've ever had in my entire life. I just want to run on the beach singing about it because we're, right, that's how we are. You'd be like, not bad. But the word bad's in there, so it sounds negative. So a sentiment analysis program that's trying to tell me, do people like my stuff, would have a hard time when I mix those things. I talk as normal and I say, it was pretty good. Didn't like the potatoes, but the steak was great. What sentiment is that? I have no idea. All right. So this is what's in my database right now. And my mouse has decided to quit. So we'll just switch to the trackpad, which I'm not good with. So all I'm going to do here is I'm simply going to have a Java statement that simply sends out to the cognitive services. This is all the code you need. That selects from the database those same objects, sends out to cognitive services, and we have something called sentiment analysis. It expects parameters, and it's going to return something in a JSON document, which I'll tear apart and put back inside SQL Server. You can see what I've got, the ID, the review, and the sentiment score. Here's what's kind of interesting. This is what I get back. So now, instead of writing data science stuff, I can simply use it. So I wanted you to be aware that this is available to you, but it's not the main thing we're going to talk about the rest of this session. But I wanted to make sure you knew you don't have to do anything at all. We have it built for you. You pay a few cents per call, blah, blah, blah. It's the typical kind of service arrangement. Make sense? This is very useful. You can put this to use like today. All right, but you probably want to start doing some things on your own. And to do that, we use something called the Extensibility framework. What is this? The Extensibility framework is a series of programs, and basically here's the upshot of how it works. We could have put the R language inside T-SQL, and then we would have to maintain it. We could have put Python in T-SQL, and we'd have to maintain that too. We could have put other languages in T-SQL, like Java and so on, and we'd have to make that supportable too. And as things change, we would constantly be making you upgrade your version of SQL. Also, R, Python, and Java allow you to do things, a lot of things, that we don't let you do in SQL Server. We don't want to let you mess with the memory that the server's using or the hard drive, right? We don't like you doing that. We need a way to sandbox you out from that. So what we decided to do was stand up another server next to your server. So when you install SQL Server and you say, I want machine learning services, we also give you R, we also give you Python, we also give you Java if you check them off. Once you do that, they're now both sitting there. We then create a secure memory channel between them so that the data never leaves the computer itself, but now the SQL Server has a direct line to R, Python has a direct line to SQL Server, and so on. So when I put my data up in memory, R can just work with it, SQL can work with it, but they're not touching. Everybody with me so far? R can't crash the server. Python can't crash the server. Make sense? That's why we did it that way. There's some code in between there that makes sure that shuffle all works. That's the machine learning extensibility framework. It's the way it looks in Windows. We also have SQL Server on Linux now and in containers. You can put machine learning services in both of those, but they don't have the same constructs. They don't have services, they have daemons, they don't have memory channels, they've got something else, and so on. So we have a whole different architecture for this that I'm not showing. The point is they still work the same. They're side by side. They're not conflicting with each other, but they have a secure memory channel to share data. Okay, good. Everybody looks like they're kind of getting that. All right. The first process you can use with this system is something called native scoring. What does this mean? Do you remember I talked about a training session and then it creates a model? If you have done that, you can simply give it to SQL Server and point to it. And when you do, you can simply call that model for your predictions. So let's take a look at how that works. So I want to make sure you know these are always available. I think my battery's dying here. Here we go. So this is the native scoring with predict. I'm going to use master, I'm going to create a little database, and I'm going to fill it with a very controversial data set. Back in the day, there was a person who created an iris, a flower data set. And this data set for flowers was something that he used inside statistics to be able to predict whether a flower belonged to a certain class or another simply by observing some of its parameters. The reason it's controversial is it was eventually used to work with eugenics. It's kind of bad. So this isn't often seen, but it's fairly canonical. I just wanted to have that disclaimer there. I'm not promoting the IRIS data set. It's been around for 40, 50 years now. Well, the data set itself's been around for hundreds of years, but it's been here. At any rate, this is canonical, so it's easy to understand. What am I doing? I'm just inserting into that database the following columns, and so on, and I execute the script, and all I'm doing here is this. First, I tell it my language. I'm going to use R. That could be Python, that could be Java. What follows is the R or Python code. And here's the R code. And you can see here the functional nature of R. This says there's a thing called iris data, and I want it to take, this can also be read as gets, the iris data set that's built into R. So a thing called iris data is getting what is in the iris sample data set in R. Everybody with me so far? Good. Then I'm going to say there is no input data whatsoever. I'm not sending anything from SQL Server. And I'm going to output the thing I just did. Pretty impressive, no? All right, all I'm going to do is insert into a table called iris data the output of the iris data set from R. It's kind of a pointless step. You would rarely do this. I'm just using it to show you how those things work. At this point, right here, and by the way, this has to be enabled. You have to turn this on. It's not on by default. This is the extensibility framework. Doing that right there, that's the extensibility framework. The input data is your SQL statement. The script is your language data. That's it. That's all you have to know. It's that simple. Let's go take a look at this. First of all, I'm going to go create a table called ML models, machine learning models. And I'm just going to get a model version, and I'm just going to get a binary object of the actual trained model. This is the training stuff we're going to do. When we're done, we've got that little Excel formula, that thing, that's a model. So I need somewhere to put it, because I'm going to use it later. The great thing about this is I'm going to stuff it right back in SQL Server, because sometimes you create a model, it works great, and then it starts to drift over time. So you improve it. You can store it again and have a version number, because you may want to go back, or go back to see what you did wrong, and so on. All right, so that's all that is. The next thing I do is I execute a binary script, an external script. This is in R, and it gets this R code, and then it sends out the model, and that simply stores the model in an insert into the system we just made here for my scoring. Everybody with me so far? All I did was send it some things from here. So far, nothing from SQL, right? Nothing from SQL. I'm just going to go get the output. And it tells me what it does. It does the training work, and it stores the model. Now I can show the models I have. There they are. It's a big old long string. And that's how big it is. Now what I can do is go get the model out of SQL Server, and I can now apply it to a prediction. That's the way I can do this. Pretty cool, no? All right. Now that I've got that, I can do my predictions and get them back. Those can be stored right back in the database. So I've done the training, the modeling, and everything else out of the database and right back in. Make sense? Okay. Let's go back to Slide World. Now let's go to the next one. Let me recap what we saw just a moment ago, and then I'll show you another example. The first part is the SP execute external script. Second part is the language. From there, you need to tell it what you want to do in SQL. That's your typical select statements from any tables, any SQL you want, your SQL, whatever you normally do. The R part is what comes in the @script variable. And basically it says, in this case, the huge R script I have is the output equals the input. So when this one runs, if it works, it's either going to be 1 or 0. That's it. And then I say with result sets, come back with the word installed at the top and a 0 or a 1, and that's a not null. It's got to have something in it. That's it. To the side here, you can see that the SQL part goes to the green. See that? And then the other part, that goes in the blue. The R part goes to the green and goes to the R star. Does everybody see what's happening there? Okay, good. Is that clear? Makes sense? All right, good. And then I get the results back and I can do something with them. You can insert them somewhere. You can show them on the iPhone app you just wrote. Whatever you want to do, it's just SQL at that point. So there's a SQL part. There's an R, Python, Java part. And there's a SQL part. It's just a sandwich. Everybody got that? Very simple to use. And you're like, I don't know how to write that R part. Go find a data scientist. Have them write the stuff in R that they need, and they just hand it to you. You put it in between those quotes marks. You tell them, what data do you need? They say, I need these things. The neat thing about that then is that the data scientist doesn't actually have to see the social security numbers and salary ranges and so on. They just ask for the data they need. They will train. Once the model's set, you can now show other data that the data scientist never gets to see to get the prediction. As long as they're similar enough in what you trained on, you'll get accurate answers. Make sense? All right. Let's go take a look at that again, and I'll show you another one. All right. We'll use another one with R on SQL Store Procedure. I'm showing R just to be consistent, but Python works exactly the same way. So there is a interesting data set inside R, sample data set, called CARS, C-A-R-S. And it tells you, based on various things, how much the gas mileage should be in that car. That's what it did. This is very old, by the way. So there's miles per gallon, the number of cylinders, and so on. These things that we see here, the miles per gallon, is something we call a target or a label, something we want to predict or know. The other things that you see here are just called features. We would call them in databases attributes or even columns. That's the data we're after, right? So it's wanting to know, the algorithm wants to know about the cylinders, the displacement, the horsepower, the dry weight, the gross weight, and some other things, how many gears it has. You can tell this is old because it has carburetors, and actually people still shift cars. You guys still shift cars here, right? Yeah, we don't do that anymore. We're way too lazy for that. No, I have a manual car as well. All right, so we're just going to create a table. We're going to insert, this is that exact same thing we did with the iris data set, exact same thing. We're just going to take the cars, put it inside the table we just made so we have a data set to play with. Now, we're going to create a linear model here, and this is all the code you need to create a train model. This is just actually even getting rid of the old procedure. So I'm going to create a stored procedure called generate my model, execute R, and basically this is the entire part of R that does predictions for those features on the label that you want. And it literally has everything in there that you need to do that prediction. All of that's there. So once it's done, it simply gives us the train model that we have out. And once again, I'm storing the model. Now, you could have done all the work inside R and got the results back right away. You don't have to store the model. You can create a model every time. But that's not normal. Normally, you create a model and then use it over and over and over. Once you check and see that it's performant and so on. Everybody with me? Okay. Good stuff. So we update that. I'm going to go ahead and I'm going to use year, month, and hour and so on to go get my model version, so I know exactly when I made it. That's just something I'm doing, but it doesn't matter. And I'm going to create my table here. I'm going to drop the cars in. Here's some new cars that it's never seen. These cars I've never seen. And I'm just going to tell it, okay, now, go take a look at that. Go get the latest model that you like and give me the result sets with the predictions. And here they are. If I change the horsepower and I change the weight of a car, what gas mileage should I get? What percentage change should I get in my gas mileage? And this does that for me. Now, where's this really useful? You talk about flowers and cars and so on. We wrote an app not long ago for an insurance company, and they want you to be able to take your iPhone, point it at a car, and do I need to send an agent out, or do we just total it out? Do I want to send an agent all the way out there to see if your car's totaled, or can I just predict it? So we ended up with 3 pictures, front, back, and side, to see if it was totaled, and it could do almost an 80% guess at how totaled the car was, and they could just like total it out. Like literally have the wreck, get out of the car, hold your neck, take a picture, they send you a check, you go straight to the hospital. All right. Okay, everybody comfortable so far? Is anybody lost? No? You following all right? Okay, good, excellent. All right, where can you deploy this? Lots of places. We have it in SQL Server on-prem. Starts in 2017. We added Python in 2019. And now we've got in 2022, Python, Java, R, and the Extensibility framework is now open for you. We have it all the way down in the lower SKUs, all the way down to IoT. We have it in Standard Edition, Enterprise Edition, and so on. We have it inside Azure in virtual machines that you can use. This same kind of technology is built in to the Synapse tool that you see, the Synapse platform, that also has machine learning. We also have a full machine learning services in Azure that can talk to SQL Server, but is not embedded within SQL Server. You can use this inside containers. In fact, I'm running it now inside containers. So you can actually run it in Kubernetes, in containers. That means it runs on Linux, works just fine, and as you can see, even down in the chips. I want to make sure you understand that's both the data engineering, it's the training, it's the model storage and versioning, and it's the scoring or predicting or endpoint. For everything can be done right inside SQL Server. All right, there's tons of ways to learn more about this. Absolutely tons of ways to learn more about this. So I want to make sure you understand that we're not just going to drop you off. There's a full journey here. That AI school I gave you earlier has a full course led step by step as if you were a developer to do this. We have several tutorials. I want to give you one more resource that's not listed here, so you may want to write this down or type it in. I'll say it slowly. I should have had it up on the screen, but I'll just say it slowly. It's aka.ms. That's the front part, aka.ms / that's the one that leans to the right. And it is SQL Workshops with an S. SQL Workshops. aka.ms / SQL Workshops. Bob Ward, Anna Hoffman, myself, others have created a full GitHub-based learning site that you can take completely on your own, and we have everything you can imagine available there for free, and we also have all of our decks, source materials, and pointers out to the CAT team, the engineering team. All of our scripts and things are located there, and they're available to you for free. aka.ms / SQL Workshops. All right, and the last part here, I'm supposed to show you this. If you'd like to rate it, I want you to rate it. Here's why. All kidding aside, hopefully this was useful. Was this useful at all? Do you know more than you go? Okay, great. That's what's more important to me, is that you find it useful. But I do want you to fill this out for the conference organizers. I want them to get good speakers in here, because time is the one resource that you can't replace. And it's super important, if I take your time in here today, that I give you value back for it. Don't allow bad presenters to waste your time. Learn something wherever you go. If they don't repeat the question, then say, hey, can you repeat that? I didn't hear what that person... How many of you have had that? You've heard somebody ask a question, you have no idea what they said, and the presenter goes like this. Yeah, never do that. You're like, wait, what? What did he just say, right? So always make the presenter repeat the question. Also, make sure your presenters are spot on with what they're working on. All right, I think that's the end of our time here today. We're going to move forward. There's lots more to learn in this area. There's lots more to learn at this conference. Thank you so much for your time. Have a great rest of your day.